One question. If you look at this one.
All right. So this first one, let's see, X bar was 92.6. Sigma was 4.11. And it's 37. Why is it okay to use Z-scores? The real thing here is, why is it okay to use a Z-score chart to convert percentage back to Z? Is because I do have a normal curve because n's big enough. Also, you could have said, because I say so. They're normally distributed. Either way. How do you find Z? So we could use a little baby chart, but just remember 0.95, this is 0.025. You should find 1.96 again. And now I've got everything I need to throw into this bad boy here. It's 92.6, give or take. 1.96 of these. Let me say this again, and we'll say this a few times. The plus and minus is in the formula already. See that? So when you find the Z-score by hand, you normally do find the negative one, right, first. But you just care about the number because the plus and minus is built into the equation already. Yeah. You guys with that? You guys see that? Because I always get somebody put a negative here and they freak out about what that does. It's like, why do that to yourself? The negative is already there. It's in there. What do you guys get for the error here? Anybody maybe listen to me? No?
1.324.
1.324? Okay. And then if you add and subtract that, you get 91.276 up to 93.924. How's that? Let me stop there for a second. So you can write this, but don't stop here. We are farmers. No. 95% confident that what? That the interval, who to what? 91.3 inches to, and again, you can round less if you want to. Leave your friends behind. All right. Does what? Only a comma there. Contains the true mean length of dolphins. And I think I tried a basis. I looked up dolphin lengths and I got some numbers, and that's where the 92 came from. 4.11 I completely made up just to be honest. Yes?
Is it okay to write population mean?
Yes, good. So I like you said that. When I say true, I'm not gonna not be able to say true. This is why I don't teach English. Because it's just, I've always said that. I think my teacher said that, but what we mean when we say that is the population mean. So anytime I take a sample, I know. So if I just said, I think that the mean is 92.6, in a sense I'm right because that's the best guess I got. What a confidence interval does is it improves on that estimate. So so this is what we got. What do you guys think just looking at this? Is this pretty good? What would make it bad? What if another group got 80 to 107 for their interval? Is that better or worse? Which one of us seems to be more certain about what we found? The top one, right? Because it doesn't go. If somebody's like, I don't know, how far away do you live? Oh, where am I? It's somewhere between 2 miles and 30 miles away. What the shit? You guys with me? It should be more like somewhere between 10 and 13 miles away. Okay, that's a normal human response instead of, I'm either at home now or 50 miles away from home. That's one of those, somewhere in there. You guys with me? No.
Even though it's less accurate, wouldn't they still be a little bit correct? Because they
Yes,
still
I
have
didn't say they're wrong. I never said they were wrong.
Okay.
I'm just saying which one is better. Which one gives an air of being more certain is this one. Right? Now, at the same time, you can't always be so certain. So sometimes your confidence intervals will come out less than ideal, but oh well, that's the best. So that is still doing a good job. It's communicating the uncertainty in what we're trying to measure. Yes? Maybe?
Yes.
Okay. So that, and again, if anybody who's wondering where those come from, my brain, it was just an example, all right? I always get somebody, where did that come from? No, I didn't get 80 from this. I just made it up as another group. Okay. Now this one here, would a 90% confidence interval be wider or narrower, which is another really good word? Wider. How much did we catch with the first one? Do I want to catch more or less with this one? So would I cast my net out wider, or would I catch my net out a little narrower? Narrower. Yes, I only have to catch 90% of the information now. I really want this to make sense. So when we do this, we caught 95% of all the average lengths of 37 dolphins. So that's why we are 95% confident that this interval we created catches a specific thing, the true mean. How can we say that? Because we got 95% of everybody. Right? So if I went out now and I captured 95% of all Grossmont students and put them in this big warehouse, how certain am I that I caught Fred, the one kid that really, he's the guy that cut me off, I want to get him. How certain am I that I caught him? If I get 95% of all Grossmont students, put them in a warehouse, how certain am I that Fred's in there? 95% freaking sure. Do you guys see how that's exactly the same shit as this? If I catch 95% of all the dolphin lengths, of average lengths of 37, then I'm going to be 95% certain that I caught a specific one, the true population mean. Maybe it's the same thing. It really is. Well, so in this one, the only thing that changes is what? The z-scores. For 90%, we did one like this just a minute ago. What's it for 90%? What's the z? 1.645. So the formula is going to look exactly the same, except there's going to be 1.645 right there times 4.11 divided by the square root of 37. So your error is going to be a little smaller now. What's it come out to be?
1.1.
Yeah, that sounds about right. So we get anywhere from 91.49? No. Yes? 489. Up to 93.711. Right? So we are 90% confident that the interval 91.5 inches to 93.7 inches contains the true mean length of all the right? Now, here comes the nifty part. Let's go back up to part of it. When I took 37 dolphins for a 95% confidence, what error did that lead to? That led to an error of 1.3 inches, right? Roughly. If I wanted, what would I do with my sample size if I want that error to go down? And from day one we know this. How do you end up being more certain about what you see in a sample? You get a bigger sample or a smaller sample? Bigger one. The bigger the sample, the more sure you are about what you find. If you take two people and you take their average height, does that tell you anything about the average height of all people? Right? That's not a good enough sample at all. Holy shit. Got to take a much larger sample to represent people better. Maybe. So, a sample size of 37 leads me to an error of 1.324. A sample size of like 80 is going to lead me to a smaller error. We knew that day one. Bigger sample, I should be less uncertain about what I see. You guys with me? Notice mathematically, the math comes in and says, oh, you're right. Because if I make n bigger, what happens to this? If I divide by a bigger number, I get a smaller number. So yes, the error does go down when n gets bigger. So, we're going to create a formula that I call a feasibility formula. Of course I would. It's weird. What does the word feasible mean? Feasible. Feasibility? Doable. Exactly. This is perfect. So you could do a feasibility study. We want to make $1 billion next year. How feasible is that? Not. Oh, let's lower our expectations, right? So look at this last question. So I'm at 95% confidence, right? So you guys see it? But I don't want to have a 1.324 error. I want to have a half an inch error. How did I know that that was the error? Probably because that bold and underlined word. If I said guess my weight to within 10 pounds, and I weigh like 200 pounds, how far off can you be and I'd still say you won? You're all within 10 pounds of 200 is what? Up to 210, down to... If you guess anything in between those two, you win a prize, kids. Yay. Yes. And isn't that the error? Plus something, minus something, that's the error. Bless you. So it's not always going to be the word within, but it's almost always going to be the word within. That's going to be the error that you want. How do I know I want to use a formula that solves for n? I still got to prove this thing. Because what's the question? How many? Oh, shit. So I want a formula that solves for n. So where the shit did this formula come from? I don't know. Yes, I do. So help me out. Remind me. This formula here. Which part of this is the error? Which part of that? This whole thing is the error. So let me write that down. The error is this. Yes. Solve that for n. What sucks about n in this equation? Two things. Where is it? It's on the bottom, and it's inside of a... Damn you, n, with the shit. So how do I get it out of the bottom? Multiply both sides by root n. Because then what happens here? Die. So that's the great thing about solving equations. If there's something in it you don't like, most of the time you can kill it. Because you got two sides you can do shit to. That's the correct way to look at algebra. Oh, sweet. I don't like that. I'm going to kill it. All right, that's a little bit, not a good life lesson, people. All right? No. Sorry. This is not home ec or independent living or philosophy of life. It's philosophy of math. So I get square root of n e equals this. So 2 more steps and I'm done. How do we get rid of that e? Divide by e. And then finally, how do we get rid of that square root? Square both sides. And couldn't you square each of these if you wanted? Z squared, sigma squared, e squared. So now you see where that equation comes from. I appreciate all you guys write this down. You never have to do this yourself. I love you guys so much. So that's where this comes from. So, now real quick, watch. If I put in here 1.96. Why? Because it's a 95% confidence, and we know that that's 1.96. Are you guys with me so far? Yes? And then I put in there the sigma, the 4.11. If I put, this is wrong, but if I put 1.324 right there, I already know that it would come out to be 37, because I know a sample size of 37 gives me an error of 1.324. So don't do that. What should go here for E? What do I want to have happen in this problem? I want E to be 0.5. There we go. So Z squared, sigma squared, divided by 0.5 squared. So that you can see why I call it feasibility study. If this comes out to be 18 billion, I doubt there are 18 billion dolphins, so that's not feasible, right? But if it comes out to be 100, maybe we could do that. Maybe we can go sample some more dolphins, get 100 total. That's why I call it feasibility. It's feasible to try to get the error down to this much. And then let's see what we get. Yeah. What do you guys get?
259.
And this is a what? Sample size. This is a number of things, so I should probably always round this up. So it's a whole number.
Because you can't cut it off.
I don't want you out there chopping dolphins. Don't do that. They'll make a show about you, and it'll be Dexter Dolphin.
Oh, I love it.
There you go, Dexter. He only kill people that mean it as well sometimes.
She might be some bad dolphins.
Yeah, these bad dolphins, they should die. Dexter comes in there, no problem. Doesn't need to use plastic because they're in the ocean. It's all good. That's horrible. Oh, too bad. Now, last thing. Last thing. The other side we're going to do next time, I want to, that's the wrong phrase to say. Whenever you say the phrase next time, you automatically, it's like Pavlov's bells, right? Start drooling. I can leave. Stop. Pavlov's dogs. You guys know? Yeah. Ring that bell. It's up time. Last little thing. We're not going to do anything with this. I just want to get you guys to realize where this formula comes from. Also, if you haven't noticed yet, I do chapter 8 out of order. Section 8.1 and section 8.3, they both use the same distribution, z-scores. Section 8.2, we're going to have a new distribution with a new chart. Oh man, sounds good. So that's why I like to do that out of order, because that middle section introduces a brand new distribution. I'm like, why do that in the middle of shit? So let me write this. So we sort of started, I don't know if you guys realize this. This is why I should have done this the other way, but too bad. We started with this formula here, and then we tweaked it. So we tweaked and tweaked and tweaked it until we got here. You guys remember that's basically what we did at the beginning of class. All right. I want to do the same thing, but I want to end up with the formula about percentages. Because we're finally going to get the formula that tells me the plus or minus 4 percentage points that we always see at the bottom of a poll. So, oh yeah, and I forgot. Oh well. I didn't really find something, so I'll find it. So let me start over up here. So if I want percentages to show up, that's going to be NPQ business. Let me use a better. Who's working today? Are you working? That's pretty good. That's good. All right. First thing is, let's start off the same place we did before. I normally don't know mu, I know x bar. Somebody remind me, what's the formula for mu for NPQ? It's beautiful. N times P. Now here's the first little neat thing. I don't know mu, I only know x bar. P is the percentage of the population. This symbol is the percentage of the sample. And yes, it is called P hat. And yes, that's not something you want to wear. Sounds like you're on a boat and there's an emergency. I don't know why you don't just pee on the side. You're in a theater. Give me your hat. No. So, that means that the sample would actually be NP hat. Do you guys get the idea of that? So I'm going to replace this with NP hat. What was sigma? So now it's going to be square root of NP hat Q hat. What's P hat plus Q hat? Still 1. What's P sock plus Q sock? 1. I don't care what articles of clothing they're wearing. P and Q have that same basic idea. One's probably a success, the other's probably a failure. These guys just happen to be wearing hats. And I still think the hatted ones would make a great band. The hatted ones. Now, stay with me now. Whoever's still with me, stay with me. If I said this, would this be okay? What does this try to do? Doesn't this try to capture the real mean? Is that all right? You guys see what I mean when I say that? The mean, I'm trying to capture it with this. All right. So what am I trying to capture with this? So like the real mean, NP. But what did I say? I want a confidence interval that's just about percentages. So how do I get rid of the n? Let me divide the n. So that, see how now I just have percentages left, right? So I know a confidence interval for percentages should be a percentage, give or take a percentage. Like 70%, give or take 4%. So here, what do I got? I got a percentage, give or take this weird thing. All right, one more step and we got the official formula. Can I just kill those n's? If anybody could, you could. No. Can I cross those n's out? No, I definitely can't.
The Z.
No.
Part of the square.
One of them is half an n, so it's not really a full n. You can't multiply or divide things unless they have the same root. Do you guys remember that? What's the square root of n squared? What's the square root of n squared? What is the square root of n squared? N. So can't I replace n, like I already did, with the square root of n squared? Do they both have the same root now? So I can reduce this. One n cancels, one is left on the bottom. So here is this fantastic formula. That is the formula for a confidence interval for a percentage. So if you ever see plus or minus 4% at the bottom of some poll, that's this piece, plus or minus some percent. So how do I make that smaller? I can make n bigger, I can make z smaller. I got some control over that shit. So if you look at the other side of the dolphin thing, there's a problem. You can see this formula sitting up there. It's crazy. All right, that's plenty.
Are we going to need to know that?
Huh?
Are we going to need to know that?
Hell yeah. Well,